The accelerated pace of technology, like we heard in some of the previous talks, has enabled new ways for us to study the universe as a whole. Computer simulations where we can model complex physical systems inside of our computer are becoming increasingly prominent in various different fields, but definitely in the fields of astrophysics. So computer simulations like this one, done by my colleague, Dr. Nathan Goldbaum at the National Center for Supercomputing Applications, model galaxies like our own Milky Way, composed of stars and gas and dark matter. Now, every point in this visualization represents a star, and every flash represents a supernova going off as a star explodes at the end of its lifetime. The different colors represent different kinds of gas, hot and ionized, and various different forms. But before we get too deep into the cool movies, let's ask ourselves, why use simulations at all? When you look out on a beautiful nature scene, a scientist will start to ask questions, why are the things the way they are? Why is the vegetation green? Why is the water blue? Why does water appear liquid here, but it's frozen in the form of snow on the mountain and then in vapor in the form of clouds in the upper atmosphere? And the way in which science addresses these is through experimentation. Most science is experimental. You'll come up with a hypothesis, you'll test that hypothesis through a carefully created experiment, and then you'll analyze those results and come to some sort of conclusion based on the experiment that you conducted. But in the field of astrophysics, the study of the stars and galaxies and everything in outer space, it's not experimental. I can't propose a hypothesis that that disk galaxy is the way that it is because of its proximity to that star, because I can't conduct an experiment where I put a galaxy over here and then put a star over there. I just don't have the power to manipulate galaxies and stars, and probably neither do you. But in computer simulations, we can create a virtual volume inside our computer program and manipulate things with godlike powers and move things around, and then move forward in time and see how our experiment takes place, and then draw some sort of conclusions from that. So we can run virtual experiments. Furthermore, when we look up in space, we might see, this is the Hubble Ultra Deep Field with many different kinds of galaxies present. You see red galaxies, you see blue galaxies, you see disk galaxies, you see spherical galaxies. And you might ask, as a scientist would, are these intrinsically different structures, or are they different phases of the same structure through different phases of its life? And computer simulations allow us to artificially accelerate time in our virtual box for much longer timescales than we might live in our lifetime, or even than civilization has been around over a couple thousand years. And so we can answer these sorts of questions. We can gain some sort of insight over the natural world. And finally, because we can artificially accelerate time, we can accelerate it into the future and effectively predict the future based on the physical laws that we know that are present. So we can predict when an asteroid is going to strike the Earth, or what the solar system is going to look like in 100 years, or 1,000,000 years. So how do we actually simulate these physical systems? We create, as I said, we create some virtual space inside of our computer. Here I've just represented it as a grid of array elements. And then we program in the dominant physics. We can't program in all the laws of physics in these simulations because it would make them too complicated and our computers would just grind to a halt. So we program in the dominant things on these scales, which are primarily for astrophysical systems, gravity, the same force that holds us to the surface of the Earth. Gravity is an attractive force, so it isn't just holding us there. We're actually pulling back on it. Gravity is pulling the Earth back towards me, but I don't weigh as much as the Earth does, so it doesn't move very far. But it also pulls stars together as well, because it's attractive. Pulls anything that has mass together. So we include gravity in these simulations, and we also include fluid dynamics, how fluids behave. Because most of the baryonic matter, the normal matter in the universe, is in the form of fluids. Not a lot in solid structures like you and me and this wood. It's more in fluids. So whether it's the fluids of the waters or atmospheres on our planet, or on Jupiter, or even in distant nebulae and star-forming regions. Most of it's in this fluid, gaseous plasma form. So we program those into our simulations. We start with some initial conditions as the starting point of our simulation, and then we artificially accelerate time to allow, this is just some arbitrary uniform grid of stars, and after our simulation is run forward, it gives us a different configuration of stars. And finally, we compare what we get out of the simulation with something about reality to garner whether or not our simulation was accurate in any capacity, or if we can just throw it out and say that that was garbage. Because ultimately, what we do in our simulations has to reflect back on reality, right? That's what we care about. OK, so what sort of things do we simulate? One thing that we can simulate is the evolution of large regions of the universe. This is a simulation I ran a couple of years ago on a supercomputer. And early in the universe, it was very hot and very dense and kind of like a uniform fog of material, although much too hot. You wouldn't want to walk through it. But there were very slight overdensities, very slight regions where it was overdense. And over time, gravity starts to attract. Remember, it's an attractive force. It starts to attract things onto those overdensities, and it enhances them. And you start to see the buildup of structure, what we call the cosmic web, because it looks a bit like a web. And over time, this is going over the 14 billion years that the universe has been around, you start to see this kind of web-like structure consisting of walls and filaments of material. And where those filaments cross at these nodes, that's where structure builds up, and that's where stars form, and that's where galaxies form. That's where things like the Milky Way galaxy, our own galaxy, exists. It's in one of these little nodes. And if we zoom in on that, and before I get to that, to further show, this is a visualization taken from observations from the Sloan Digital Sky Survey of the actual locations of galaxies in the universe. And what you'll notice is galaxies aren't uniformly distributed throughout the universe. They're clustered. They're clustered, and they're clustered in these same filaments that we saw in that simulation. This is where we are comparing the results of the simulation against real observations and saying, holy cow, guys, they actually match up pretty well. The simulations, even though we just predicted it on theoretical grounds, they're reproducing what we see when we look up with our telescopes in the sky. That matter and galaxies are clustered and not just uniformly, randomly distributed. But if we zoom in on one of those filaments of matter and follow, in another simulation, follow the evolution of the buildup of a single galaxy, we can gain some more information. So on the left, we're just looking at the distribution of gas or material in a large region of space. And on the right, we'll show the temperature of that gas. The yellow stuff is hotter. The red stuff is cooler. And so what we'll see, the white circle represents the gravitational influence of a single galaxy. This is our filament. And all those little nodes are individual galaxies that are falling down onto the primary galaxy. This is like our Milky Way. And as it absorbs these systems, that cool gas falls onto there, and it turns into stars, and then hot gas. And it blows out in these yellow plumes of material, hot gas winds that are exploding out of the galaxy. But this gives us a lot of insight. It tells us that galaxies, even though this is taking place over 14 billion years, much longer than we could observe with our lifetimes or our civilization's lifetime, it's telling us that galaxies build by eating their neighbors. They're cannibalistic. They build hierarchically by absorbing smaller galaxies. I'll play this again. By absorbing smaller galaxies that are gravitationally pulled into them, they eat them, and then they eat their cool gas. The red stuff turns into stars and supernovae, and it blows out in these hot winds. And that's how we build up a galaxy. And the output of these galaxies looks something like this. This was from the same simulation that we just showed, done by myself and colleagues here at Caltech. So this is flying into a galaxy as it's evolving, and we're looking at it in starlight. So the blue light is coming from stars. The red regions are dust lanes that are absorbing the light, the blue light preferentially, just like if you look at through a dust storm, you'll see it appears very red. And this is the buildup of a disk-like galaxy like our own Milky Way. But we also, as we talked about, we want to predict the future, right? So our galaxy, the Milky Way, is just hanging out. It's much like the galaxies that we've been looking at in the last two simulations. It's this disk-like structure. But it's not the only galaxy in town. We have two neighbors, the most massive of which is the Andromeda Galaxy. Maybe you've seen it when you've looked up on a dark night sky. And it turns out that we're on a collision course, the Andromeda Galaxy and the Milky Way galaxy. Now, don't worry. This is going to take place 5 billion years in the future. Don't sell your real estate. But these things are going to collide. And when they collide, again, this is just really including the effects of gravity and fluid dynamics. They do this dance as they absorb into each other. Don't worry, that guy's just in the background flying past. They accrete onto each other and coalesce into a single structure. And because astronomers aren't very creative in their naming schemes, the combination of Milky Way and Andromeda makes Milk-omeda. It's a nice portmanteau there. So our future galaxy in 6.5 billion years will be this very different type of galaxy called an elliptical, because it looks more like a hard-boiled egg as opposed to the nice disky structure that we had before. And it's much redder because it doesn't possess any young star formation, which is primarily in the form of blue stars. So that's what we have to look forward to in 8.2 billion years. Anyway, my points are, what are simulations? They're a way of representing some physical system in a computer program. And the larger the computer, the better you can do this, the more sophisticated your model can be. We run them in order to run virtual experiments on things that we can't necessarily experiment with in real life, like astrophysical systems, and to predict the future. And finally, we simulate all manner of things. I primarily just showed galaxies in the universe, but people do this on a number of different topics, and not just restricted to astrophysics, on all sorts of fields. So I encourage those of you in the audience who are still in school, mathematics is good for studying, obviously, physical sciences or medical sciences, but also computers. I mean, everybody has a lot of experience with computers, but I actually studied computer science as an undergrad, even though I'm now a professional astronomer and astrophysicist, and it served me very well, being able to code. There's almost no subject matter in the field of science that you can do without interacting with a computer in some way. So having some background in being able to program computers is beneficial. For more of these movies, you can check out my website, or feel free to come to any of our free public lectures at Caltech in the astronomy department. Once a month, we have free lectures, and we have telescopes set outside. I hope you enjoyed the burned marshmallows today. Thank you very much.